Great pleasure to introduce to you now Professor Jeff Forshaw from the University of Manchester, the black hole information paradox, black holes, and why they are so important. Thank you very much.
Thank you. Thank you. It's lovely to be here. You've all had plenty of time to read the quotes at the front, and in part, trying to explain in what sense these quotes are appearing, as indicated by recent research in theoretical physics, appearing to be close to being right. So there's some substance in these quotes. The idea that space is emergent in some sense. So what I want to do is go back right to the beginning and talk about how it is that black holes, and in particular the black hole information paradox, have been the catalyst to this recent research. It's also, the stuff I'm going to talk about is also a kind of, a lot of it's inspired by the work of Stephen Hawking, and it's, I think, in part a tribute to the brilliance of his research. So let me start with the statement, basically an explanation of what black holes are. So we're going to talk about black holes. I'm not going to be so interested in black holes from the astrophysical perspective, like how they're formed and where they are in the universe, and how they operate within the context of the universe at large. I'm going to be talking about more theoretical aspects of black holes. But black holes do exist, and for quite a while after Einstein had, Karl Schwarzschild, very shortly after Einstein had written down his equations of general relativity, had already identified a solution which we call now the Schwarzschild solution, which basically is the solution for a black hole. And not much longer after that, it was appreciated that there was this possibility of black holes. And for quite a lot of the community through the 1930s, 40s, 50s, didn't believe that they would actually exist because they were too absurd. There's a great quote from Arthur Eddington, which I've forgotten, where, with the word absurd in the context of black holes. But we've got photographs now, so they do exist. So these are nice pictures to show. The first black hole to be seen was this one on the right, which is the one in Sagittarius A star, which is much bigger, 1,000 times bigger than the one in the center of our own galaxy. So these are supermassive black holes with, this is the M87 black hole, which is the one in the center of our galaxy, and this is, sorry, the other way around. This is the one in the center of our galaxy, and this is the one in M87. So the one on the left is the one that's 1,000 times bigger, which is why it was seen first, basically, even though it's so far away. My first reaction to seeing these pictures was that they're a bit blurry. Suppose you can't have everything. Yeah. And we've seen lots of much smaller black holes through in particular, when they merge. So there are lots of instances across the cosmos of binary systems, two stars orbiting around each other. And black holes can do that. Black hole can orbit a neutron star, and they can spiral and coalesce. And that, when that happens, generates a lot of gravitational radiation, and that's detected here on Earth by these magnificent interferometers, which the LIGO collaboration's interferometers, which are like 2 kilometers long, and they're measuring actually the mean distance between the mirrors to an accuracy of much less than the diameter of a single proton. It's the mean distance, so you can do that. It's a phenomenally precise experiment, and through that, actually measure the dynamics of black hole collisions. So we're at the point now, and this is recent. So there's a kind of, from the astrophysical side, there is we're entering into an era now where black holes are part of the story. So black hole astrophysics, that's certainly a recent thing. But I'm not going to say anything more about that really. This is my one slide on general relativity, which we'll need. So I could probably kind of just show that and then just move on, really. But so the idea that gravity is essentially a distortion of space. The idea that space can be distorted is unusual, but relatively simple to appreciate. So if we were flat, if we were two-dimensional, doing such a thing, but going down to 2 dimensions is helpful because we can imagine the third dimension. We can imagine the third dimension. We couldn't if we were flat, if we were little flat creatures. Just chuck the Earth out of this picture here, and then imagine that the space is the graph paper thing. And traveling in a straight line on this space, if you always march along one of these straight lines, you'll end up flying around in a curve, what looks like a curved path in 3 dimensions. That's curved space. It's the idea that the geometry of the space is not the geometry of Euclid. Simply that. And the geometry is dictated by the energy and momentum that is present in the space. So here we've got a kind of a caricature, a cartoon of the Earth distorting the space around it. And it's space and time that get distorted in general relativity. So that's general relativity. That's a nice, simple theorist picture of a black hole. The edge is something that I am going to refer to this thing as the horizon. So there is an idea of a place, right? A surface in space. That's not what the horizon is technically, but we can think of a place where if we traveled inside of the black hole, we'll never be able to get back out again. And light, nothing can get outside of this black hole once it's passed inside the horizon. Okay, and that's simply because the gravitational the gravitational force is sufficiently strong that if we were to try to shine light out from inside here, it would just bend back and fall back in to the black hole. So is this the idea? This kind of idea goes all the way back to Laplace, who introduced the idea of dark stars, and Jean Michel, who was I think a cleric in the 18th, 17th century, 18th century. So it's a very old idea that there should be these kinds of stars. The idea that they emerge in Einstein's general theory of relativity. So what I want to show here is this is an important picture to set the scene for the absurdities inside of a black hole. So we'll talk about the singularity of a black hole a little bit. So what I want to do is give some sense of what that is, right? And the way in particular, it's not. If we go back to here, it's not the middle of this. In a sense, it's the middle, but there's something very interesting potentially happening at the middle of the black hole, right? The singularity isn't a place, right? So here's, you get this picture. This is, I said imagine being flat. Well, let's imagine being, okay, I think it's dying on me. Imagine being flat, and that could be you and me outside of a black hole. The shaded bit would be the horizon of the black hole, right? And we're kind of we're constrained to slide around on the graph paper thing. The space actually carries on. It flattens out and goes out forever at the top, and it does the same at the bottom. It goes out forever in every direction at the bottom. So this is a picture of a particular solution to Einstein's equations, not one that we think is realized in nature, well, not at least on large scales. The thing in the middle is what I'm going to talk about. It's a wormhole. But what's interesting about this in the first instance is that these two people who can kind of walk around the horizon of the black hole, right, if they had long arms, they could kind of wrap their arms around and kind of embrace the hole, right? The idea, and for them, the space, they don't see that the space is kind of fallen in like this. Like for them, they think, well, the hole's this big, right? But there could be an infinite area, in this case, area, right, inside the black hole. So there can be an infinite volume inside of a black hole. I could have a black hole in my hands now, and inside that black hole, there could be an entire other universe. And the way that's coming about, can you see how it's working? Imagine that these two little stick people were on a flat sheet, then, the distance between them would be described by Pythagoras' theorem. But what we've done is stretch the space out. We've pulled the space down so that we can create an awful lot of space inside the horizon. And in this picture, there's an infinite amount of space. There's kind of another horizon at the bottom, another universe, if you like, at the bottom here. Such things, should they exist, so in the case of wormholes in the context of Einstein's general theory of relativity, if we were to try to jump inside this black hole and try to travel through to the bit at the bottom, what happens is this is a dynamical thing. Once we get inside the horizon, it starts to stretch out. And it stretches out. And so can you imagine this thing stretching out? So it's like taking the top and the bottom, pulling it apart. It's a bit like stretching chewing gum or something. Right? The space stretches out, gets thinner and thinner and thinner and thinner and thinner. The people who are going in, their feet get further away from their head. Everything gets stretched, and then disappears. The space disappears. That's the singularity. It's the moment when space ceases to exist. So it's more a moment in time than it is a place. Right? It's what happens. It's what that is in Einstein's gravity theory. That is it, right? There is a singularity at the center of a black hole, and that's what I've just described. Right, so for the second half of the talk, I'm going to talk about three things so I'm going to talk about the information paradox. Right? I'm going to show how, so for the first bit, space is built from elemental jiggling things, is something that was appreciated by Hawking and Penrose and people. Well, I don't know actually if Roger Penrose, is he here? I don't know if he would what the actual statement, it's something that came from the early 70s. This is work in particular by Hawking and collaborators. And which has given, impetus to research in string theory. And I'll then talk about the way in which the solution to the information paradox is connected to an independent piece of physics developed by Argentinian theorist Juan Maldacena, that there is a holographic principle at work in the universe. And more recently, in an attempt to understand the holographic principle, it's become clearer that the holographic principle works, right, in a way that is not dissimilar from the way we're trying to solve the error correction problem in a quantum computer. So if I was being completely facetious, I might say, or flippant, I might say that it's as if we live inside of a giant quantum computer. And that giant quantum computer is constructed in such a way that it's holographic. And it's the holographic nature which gives the redundancy to the robustness to this quantum computer. So I'm going to try and explain those points now. The setup for it all, is the information paradox. But first, the jiggling things thing, right? And this connection, right, between the dynamics of black holes, general relativity, and thermodynamics. So this is the one slide that I've got on that, right? So the equations of thermodynamics on the left, right, and the equations of black hole mechanics, as they were called, by Hawking et al., on the right. The calculations on that right column are purely general relativity. They are calculations. So we know that general relativity, you've seen, I've said that Einstein's gravity theory is a theory of geometry. That's what it is. It's a theory of geometry. And what this slide illustrates is it's a theory of geometry, but it is also the theory of thermodynamics. In other words, general relativity is thermodynamics, which is very profound, right? And that didn't escape the attention of the people who were working on this at the time. You can just read off the analogies here for the zeroth law, the first, second, and third law. Right? So if you look, just replace the symbols on the left and the right-hand side. You can do it consistently. So you can replace the area of a black hole A by entropy in thermodynamics. So the entropy increases, second law of thermodynamics. The horizon area increases is the second law of black hole mechanics. Likewise, the temperature can't fall to zero is the third law, and it's the surface gravity can't fall to zero in black hole mechanics. So when this was first appreciated by Hawking and collaborators, they thought it was an accident. They thought that it wasn't really true. It was just a coincidence that, that general relativity looked like this. And then Stephen Hawking discovered that black holes do in fact have a temperature. So everybody thought that the black holes, objects that have temperature radiate. They radiate photons, for example. And but look, everybody knew that black holes didn't do that, so they couldn't possibly have a temperature. So this must have been just a completely accidental coincidence. And at the point when Hawking actually realized that black holes do radiate and do have a temperature, and that temperature is the surface gravity, in one of the most understated statements in a paper, he said, we thought it was an accident, I'm paraphrasing, but it seems there may be more to it than this, was his statement. So, this is Hawking's tombstone in Westminster Abbey, with the temperature of a black hole. And it begs the question then, so if general relativity is thermodynamics, and that's a literal is, right? But yet general relativity is a classical theory of a smooth space-time. Well, there was a big argument at the beginning of the 20th century, which drove Ludwig Boltzmann, to a terrible state, where he was making this very same statement in the context of thermodynamics by saying that the second law is not an exact statement, it's a statistical statement. That was not accepted at the time. Ernst Mach was determined to demonstrate that Boltzmann was on the wrong track, and it's the same situation here, right? So Boltzmann was saying the second law of thermodynamics is an emergent property of the dynamics of these small jiggling things. He just needed a few assumptions to say that the energy is basically being shuffled around, the degrees of it's being shuffled around at random. And with that, he could demonstrate the second law. So second law didn't need to know about the details of the jiggling. That's kind of important for what I'm about to say subsequently. So general relativity, which looks like a completely deterministic fixed theory, is, right, if you take it seriously, what we've just appreciated, is really an approximation to an underlying statistical theory. That's what is suggested straight away if you take seriously the laws of black hole mechanics and their identity with the equations of black hole thermodynamics, with thermodynamics. And what we're going to see now is that is supported by what we understand, in particular within the context of the solution to the information paradox. One note, right, the idea that the entropy is the area of a black hole, right, when we understand, I won't talk about the interpretation of entropy, except to say that the entropy is basically, how much do I have to tell you about a system that you don't know in order to completely specify what the system is? How much information do I have to give you to specify that system, given that I only give you some gross information? The entropy is essentially that amount of information. So it's characterizing how much we don't know about a particular system. So if we throw things into a black hole, right, the more we throw in, the black hole, with that information is lost forever. But it's as if that information is not just proportional to the area of the black hole, it essentially is the area of the black hole. So there's a connection between all of the information that went into the black hole and the area of the black hole event horizon, which is that black disk I showed was in 2D. This is like a 3D version, and the information is being encoded on the horizon. That's important potentially as well. What are all these little ones and zeros that I've drawn here? I'm kind of inviting you to imagine that information is being encoded up on the horizon of the black hole. Right, on to the information paradox. Right, let's concentrate on the top half of this slide. Right, a book is burnt and information is not destroyed. That's the technical sense in which I want to talk about information, in that obviously it's very difficult, impossible to actually read the book once you've burnt it, right? But the information has not been destroyed in the sense that it's just been dispersed. Okay. Now, if you could utterly destroy the information, that would be a thing, right? Now, the way I'm about to describe this, I'm going to talk about it as if the destruction of information per se is kind of a bad thing, right? And you might say, well, I don't really buy that. I mean, maybe you can just destroy information. But I'm paraphrasing I could have phrased this in terms of quantum mechanics and unitarity. And so the idea that quantum systems evolve under unitary evolution is the way that we might talk about this if we were talking about it slightly more precisely. But I don't want to do that. I just want to talk about it so when I talk about information, I'm really talking about it in the context of is the dynamical evolution unitary or not unitary? And the bottom picture shows the kind of situation that, the situation that occurs once we appreciate that black holes evaporate, and if we suppose that the radiation that comes off is completely featureless, so it's perfect black body radiation. It's already smacks, when you think about it in the context of what I just said about general relativity being a thermostatistical theory, the idea that you get a perfect black body spectrum from the evaporation of a black hole, is that a consequence of the fact that we've oversimplified on the general relativity side? Right? It's suggestive of that already. So let me say, so I throw the book into a black hole, it's gone forever, right? And radiation comes out. And eventually the hole will evaporate. As the black hole evaporates, it shrinks, becomes smaller, and then disappears. So you end up with a whole pile of feet. You trade the black hole, which has got the bulk and everything else that was thrown into it. You trade that. Sometime later, it's just featureless radiation from which you could never extract, no matter how clever you are, no matter how big your computers were, you could never extract the information from the book. Is that true? The modern research says, no, that is not true. That you could get the information from the Hawking radiation, that the information is encoded in the radiation that comes out. But that is, so that the information paradox is basically the statement of, does that happen? Does the information come out in the Hawking radiation or not? More technically, it's a statement on the von Neumann entropy of the Hawking radiation and how it depends upon time. Does it vanish at late times or not? So can we destroy information? Right, so this sets up the holographic picture. So let's focus on the picture on the left. The picture on the left is this book again, being thrown into the black hole. A book is a kind of like, it's kind of a little symbol of information, right? It's kind of, so the book gets thrown into the black hole. On the left, actually, shall we do let's do the one on the left first. So the one on the left requires some information that I've not told you yet, right? So I'll tell you as I go. The little rocket ship indicates somebody who is hovering outside of the event horizon of the black hole. They're not falling into the black hole, they're fixed in their position relative to the horizon. For this person, nothing that is thrown in ever actually goes through the horizon. It approaches the horizon, and it takes an infinite amount of time for it to fall through the horizon. So that book that's been thrown in never actually goes through the horizon, as seen by somebody in the rocket ship. Right. Now, this is, just to make it a bit dramatic, right? Things that are hovering very close to the horizon of a black hole experience a very large temperature, something which is known as the Unruh effect. So it's a very unusual counterintuitive effect. If something accelerates, the Unruh effect is present in ordinary space-time, like the space that we're in now. It doesn't need black holes. If a thermometer would be accelerating through this room, it would experience a small temperature, even if, it would, of course, because there's air in the room. But if we sucked all the air out, right? So an accelerated thermometer in a vacuum would experience a temperature which is proportional to the acceleration. It's a tiny effect and it's never been measured, right? But in that temperature, very close to the event horizon of the horizon of a black hole, the temperature actually, it gets larger and diverges, in fact, at the horizon of the black hole. So this is an effect that is not unrelated to, although the precise connection with Hawking radiation is not, it's not quite as clear as one might think. But the book falls onto the horizon, never passes through the horizon, and the horizon is a hot place. So one might conclude that the book gets burnt up and all its bits and pieces come out with the Hawking radiation. You might suppose that's true, and it's like, well, that's good. There's no problem then. The information does come out, right? The book never even actually went through the horizon. It gets incinerated, spread out across the horizon, and just is emitted in the Hawking radiation. The picture on the right is the picture from the perspective of the book. So we don't really need the house, but it's kind of, you might jump in with it, right? So you jump in with the book. There is absolutely nothing special about the horizon. This is a feature of general relativity, which says that if you're in inertial free fall, if a point-like object in inertial free fall experiences no forces whatsoever, it's called the equivalence principle. And as far as we can tell, that's correct. So it means, we could be falling through the event horizon of a very, very large black hole now. And we wouldn't experience anything. Right? So if we actually falling through the event horizon of the black hole in M87, I think we've got about a day. So we've got a few hours before we start feeling a bit stretched. And so the book in this case, well, it starts to feel stretched because it falls through the horizon, feels stretched, and encounters that singularity I was talking about. So this is a book which is the same book, right? In one case, it's got burnt up on the horizon of the black hole, so to say. In the other case, it's gone inside the black hole and fallen into the singularity. Which is correct? And the current thinking is that they're both correct. That two versions of macroscopic reality which are, in fact, allowed. They're not obviously in contradiction in that anything that's outside the black hole anything that falls inside can't get back out to talk to the thing outside. So the person in the house can't rush back out of the black hole and talk to the person in the rocket ship and say, I've seen the book, it went inside, right? It can't do that. So there is no way of actually demonstrating we only have an issue with this because we're trying to suppose that reality has got a single, there's a single instance of the history of this book. It can't possibly be burnt up and spaghettified at the same time. So why do we think that both are true? Right, so this comes back to the idea of the information being encoded on the event horizon of the black hole. So based not much more than on this observation, Gerard 't Hooft and Leonard Susskind postulated the holographic principle. Sometime before, Maldacena actually demonstrated that there was a form of the holographic principle in a particular string theory. The string theory is probably irrelevant, right, from the perspective of it's a bigger idea we now understand than so it was discovered technically in one branch of theoretical physics, but now this principle has been discovered all over the place in theoretical physics. It's not got anything to do with anti-de Sitter space, for example, right? Or it doesn't appear to. So this is the idea, right? Well, in fact, I'll tell you what Maldacena actually said, right? Basically, let's have a look at this picture on the left, right? The disks, so we're going to hear about, if you're at the dinner later, you can hear about these Poincaré disks maybe. Escher was very interested in this particular representation. So this picture on the left is a picture of anti-de Sitter space, right, in 2+1 dimensions. That's to say 2 space and 1 time. The disks are spatial slices and then as time goes up. So at the very bottom, we're at early times, and at the top, we're at late times. And in this particular picture, a black hole is formed and evaporated. That's kind of as time evolves, right? So there's some interesting general relativity plus other physics, right? Maybe some field theory happening inside this cylinder that we can visualize. It's an interesting cylinder. Its time is running up. Right, the sides of the cylinder exist in time. What Maldacena discovered is that there is an entirely equivalent description of the gravitational theory in the interior that makes the black hole, which is not involving general relativity at all and is purely quantum mechanical. So general relativity is a classical theory. It's not quantum mechanical, right? But it's possible to construct a theory which is a gravitational theory, starting from a theory which is purely quantum mechanics. And the quantum mechanics theory only lives on the boundary of this cylinder, right? So you might like to think of maybe think of a gas on the boundary, right? So that theory is actually a one-dimensional quantum mechanics theory in this picture, and that this has been demonstrated in the context of a 1 + 1 dimensional quantum field theory, right? So there is a gas on the boundary, so on the disk, and each disk there's a gas which is basically dynamically existing only on the disk. That quantum field theory on the boundary of the cylinder is equivalent to the theory on the interior. So that's the statement of the holographic principle, which is quite remarkable, right? It's very suggestive that gravity is something which emerges out of quantum mechanics. It's also consistent with this black hole complementarity idea being correct. The idea that there are two completely, apparently very different descriptions. So in one case here, we've got the black hole interior being described by general relativity, and the equivalent theory is just a thermal theory of a gas on a circle. It's a completely different theory, right? It is a thermal state. The black hole in the middle is actually a thermal state on the boundary. Right? That's very reminiscent of that kind of thing, right? Where the picture on the left was basically the book being distributed across the exterior on the boundary of the black hole. So I want to finish off with so we've got this picture now that the information paradox, we still don't know if it's correct or not, right? That seems like, does the information come out or does it not come out? Right, we've not answered that question, right? It's recent physics. This picture on the left actually indicates that the information does come out. That the picture on the left, and Maldacena's work, was the reason that Hawking changed his mind and did conclude, and he had a bet with, I think, John Preskill that unitarity was violated in quantum mechanics, and he was violated as a consequence of the black hole information paradox. And this picture, because the theory on the boundary is completely quantum mechanical, it evolves unitarily. There is definitely no information loss on the boundary theory, so there can't be any information loss on the interior theory. I mean, how that works is the subject of modern research. How is it that the interior, the information coming out in those Hawking particles, those little wiggly lines coming out, which are the Hawking photons from the decay as the black hole evaporates, how is it that they are encoding the information of the stuff that went in? And that's what I want to finish off talking about, right? So how does this work? How does the world as a hologram idea, how does it work? How does Maldacena's idea work? And I'm not going to go into much detail, right? But it's a consequence, as we now understand it, of quantum entanglement. So this is a nice picture from a popular article by Canadian theorist Mark van Ramsdonk, which I recommend anybody to go and read if you want to learn a little bit more about. It's only a few pages long. The title of the paper is probably something like that, Quantum Entanglement Builds Space. So what we've got here is a sphere, right? So the top left picture, we've got a sphere, and we can split the sphere into left and right halves. If the left half, imagine we put a gas on the sphere, right? So we have a gas that only lives on the sphere. When we think like that, there doesn't even need to be an interior to the sphere. It doesn't need to have an interior. We naturally think of there definitely being an interior because we try to embed everything all the time in 3D. But there could be a two-dimensional surface with a gas on it. One half of the gas is maximally entangled with the gas on the right. So there is a particular thermophile double state, if you like, which is a state where you maximally entangle the degrees of freedom on the left and the right. So I've not talked about what quantum entanglement is. Right? I don't have time. Right? It's a feature of quantum mechanics. Right? So the left and the right are, in some sense, correlated, entangled quantum mechanically. Right? If they're very maximally entangled, then there's a theorem due to Japanese theorists Ryu and Takeyanagi that says the minimal surface connecting the two halves is maximal in its area, right? And it's because we've got maximal entanglement, which is what that shaded disk is. That's a circle, right? As I slice through the disk in the two halves. So maximal entanglement leads to a geometry which has got maximum area in the middle, which is this spherical geometry. This is not absolutely literal, this picture, because the geometry of the boundary theory can't change. But it's pretty good at getting across the point about the entanglement. If I turn the entanglement down between the left and the right, then the area of the bit in the middle has to come down, right? Which is what I'm showing in the second picture on the right. What I'm doing is changing the geometry of an interior region, right? And geometry is general relativity, right? So basically what I'm doing, I'm creating an interesting geometrical theory in the interior by adjusting the amount of entanglement I've got in the boundary theory. And that is what generates the holographic dynamics of Maldacena. And if there's no entanglement between the left and the right, the two spaces become disconnected from each other. So the idea that space itself is basically a feature of entanglement in quantum mechanics. And in this way, if you kind of go the other way around, then you kind of imagine that you can kind of sew space together, right, by entangling degrees of freedom. That's a little bit about entanglement, which I'm not going to talk about, except just to point out that a 300-qubit quantum computer the physics of a 300-qubit quantum computer could never be classically, you could never simulate it on the classical computer because you would just simply need 2 to the power of 300 bits of information, basically, to do that, which is more than there are atoms in the entire universe. So there's something very rich about quantum mechanics. That's the kind of point that I wanted to make here. That richness of quantum mechanics is what we want to exploit when we build quantum computers. We want to and in an attempt to try to understand how entanglement builds space, and really being faithful to the idea of tiny jiggling things, these authors here, Pastaski, Yoshida, Harlow, and Preskel, have come up with this is not a full theory, this is just a simple little model, just to illustrate how they can get the holographic idea, right, through a system of qubits. So the idea that space might be an emergent thing out of quantum mechanics means that the fundamental theory may be a set of objects that don't live in space. Right? They're just a set of objects with relations to each other. So it's a zero-dimensional theory in space. Right? And the entanglement of those objects, right, somehow builds space. This is an example of how to do that. So the circles on this are all qubits. Right? This is an error-correcting code, a really good one. Right? Error correction is basically the idea that you're trying to do something in a quantum computer with you're trying to calculate something, and you want your qubits, the quantum generalizations of ordinary classical bits. You want them to have high fidelity. You don't want them to change, right? You want to know what state your qubit is in, right? Or you want it not to change its state, right? And the way to do that is to basically network lots of qubits together so that you can start destroying qubits and still not destroy the qubit in the middle. Right? So you want some kind of redundant way of encoding the information that you want to preserve. This is a very good way of doing that. And it does it holographically. That's the really cool thing. I've not got time to go through how it is. So basically the little white circles on the edge, right, you can strike out, destroy quite a lot of them, and you won't destroy the qubit in the middle. It's very robust. Right? But this entangled network here is very similar. It gives rise to a geometry. So it can be described geometrically. Right? So I'm kind of, I would need more time to talk about how it does that. Right? But the point is, the key point is that here we have a simple network of qubits that exhibits the holographic principle. Right? So it's an example of how this entanglement idea leads to an emergent space, an emergent geometry, and it does it, right? It does it in a way that suggests that if we want to try to find and understand the theory of quantum gravity, then the problems that we've got to tackle are in some ways similar to the problems of building really effective error correction codes. So there is, it would be quite a thing if, the most blue skies of blue skies research trying to understand the quantum theory of gravity turns out to have immense practical value in that it's related to this problem of trying to build a robust quantum computer. It also means that, see, we can build these kinds of things, not yet done so, but one can build networks of qubits. I mean, that has been done. That's like, and do experiments on them and see to what extent the holographic principle is being borne out in experiments. So the idea that the future of quantum gravity research might be on small-scale laboratory experiments tackling questions on entanglement is, for me, I think, one of the most exciting aspects going forwards. And with that, I shall stop. Thank you.
Questions?
Well, thank you for that interesting talk. The question is, we believe information should not be destroyed or should persist. However, we start off with a big bang, so initially there is no information at all, and then suddenly we have a universe full of information. Is it not the paradox that we have the information? Is the universe not actually trying to destroy the information that doesn't belong here? Because you start off with nothing, you should end with nothing. So are we just on borrowed information which should actually be destroyed? And that's what the universe is doing, is destroying information that arrived from nowhere and shouldn't be here.
There are two answers. One, the universe could be infinitely old, but that may, you can push the initial condition back arbitrarily, but there is an initial condition. So quantum mechanics makes perfect sense with some boundary conditions, some initial condition, and then the subsequent evolution of that system is unitary. So I agree that it is an interesting question to work out where the initial condition of the universe came from. Right? But the fact that once we've got it, it evolves unitarily. That's the quantum mechanics is happy with that.
Yep.
Hi, thank you. I just want to see if I've understood this correctly. So it seems that every time something falls into a black hole, its area increases, such that I presume the entropy always increases.
Mm-hmm.
This is an area is a very classical thing. It's just pure geometry. but somehow space-time seems to be used as a bookkeeping device of how much information and entropy was present in the matter that fell in, and that's a very quantum question. So why would a quantum degree of freedom, like microstates, be encoded in such a classical object, which is the area of a black hole?
It's not, that's not per se like, for example, the way that the holographic principle is thought to work now would have, right, is so general that any region of space, like this region that I'm doing with my hand now, if I could kind of cut it out, right? So I have this region of the vacuum, and I could kind of sever it from the rest of the universe. Then the entanglement between this region and the rest of the universe is proportional to the area that I've chopped out, right? So so there is a kind of area law which is natural in quantum mechanics. So it's not like there is no problem with that, right? So the entanglement entropy of like in condensed matter physics, there's a like it's well known that the entanglement entropy of some finite region is proportional to the area of the boundary of the region. So that was discovered, like that came out of studies in condensed matter physics, quantum condensed matter physics, not. So I guess I would say that there's no reason why it shouldn't. You know, it has that. You know, quantum mechanics is weird, but it doesn't mean that you lose everything. Yes, I think that's right. Yeah, I think that's what I was saying, that geometry is a bookkeeping device for entanglement. Yeah.
There's a question here in the middle.
Thanks for a really interesting talk. Yeah, the 70s were an interesting time when Hawking and his team were putting those papers out. My question actually relates in part to the previous questioner, and I was going to say at the event horizon, classically, it's a boundary at a given position in coordinate space. Quantum mechanically, of course, there's an uncertainty principle, which means that boundary can't be strictly localized, you know, the usual uncertainty principle. And that leads to some calculations which say that what are the number of distinct quantum mechanical areas that could exist on the surface, on the event horizon, and that increases in direct proportion as the area goes up, and if I remember rightly, is part connected to how much information can actually be equivalently held on the surface. So that means that when something falls in, the surface increases and there is enough quantum uncertainty, this is speaking semi-classically, to allow the information to be encoded. But perhaps you can comment on that.
So you're talking about like a heuristic derivation of the fact that the entropy is proportional to the area based on the uncertainty principle. Yeah, I think that's right. Yeah, but there are more accurate, I mean, demonstrations of that. So, like in string theory, for example, one can calculate this relationship between the entropy and the area. And in string theory, the microscopic degrees of freedom are specified. You know, so this is a theory in which you are precisely stating what the underlying degrees of freedom are, and then you get this emergent result that the entropy is proportional to the area. But we know from in thermodynamics, so you might think, oh, that means that string theory must be correct then, that you know, general relativity drops out of string theory. This is very strong evidence for string theory, and it is evidence for string theory, but it's not as strong as you might think, in that the laws of thermodynamics are emergent out of the laws of tiny jiggling things without a precise specification of what those jiggling things are. So you don't need to talk about atoms in great detail. You don't need to know everything about atoms. I mean, there are features which are important. You know, that you do need to be able to make some statement on the numbers of degrees of freedom. But basically, any system of small objects that jiggle around, share the energy around, will give rise to thermodynamics as we appreciate it. So, yeah.
Thank you. Okay.
Hi. Yeah. So the last slide you've got, that's a representation of quantum mechanics. And the very first slide you've got, the very first slide you presented with the Earth in that graph, is that sort of related? Are they related at all?
Yes,
Quantum, you're the one.
they are related, but not in the in a very one-to-one way.
No,
They're
no.
related in the fact that there is a geometry associated. The geometry is actually shown by the underlined shaded pattern here. So it's supposed to get us to think. So basically, if I if I know all of the little white circles along a portion of the edge here that coincides with one of these arcs that you can see going through the region, then I know everything. I know all the lines passing through that arc. So this line here, say, right, that's a geometrical object. We can define that geometrical object by counting the lines that pass through it. So the length of the line is determined by the number of links, right? So that's a geometry that we get. That is related to the entanglement of this thing with the rest of the system here, right? So there's a connection between the entanglement of the boundary, the little circles on the boundary, and the geometry, and an emergent geometry in the interior. And geometry was what that first slide was all about.
Relativistic geometry.
Yeah, space is geometry. I was saying basically gravity is geometry, yeah.
The question at the back.
Yeah. Hi, thank you for your talk. Just a basic question. If quantum theory, the unitarity principles, there's modifications needed to the unitarity principle and the measurement, would the black hole information paradox still hold? Or could one interpret this phenomena as basically a signal to basically try to understand quantum mechanics better? The fact that you have non-unitarity showing up in these places.
Well, if unitarity were violated, then it would mean that quantum mechanics is not. I mean, it's interesting because this. Okay, so, and then there is no necessary. That is a solution by itself to the information paradox, right?
So would the
it says the information
paradox
doesn't come out, and unitary evolution is violated.
Look,
So everything I've talked about is holding faithful to the idea that unitary evolution does hold. And quantum mechanics is correct in that sense.
Thank you. Time is very short. We have a question here.
So just a quick one on this relation. So I guess decoherence makes it hard to build a quantum computer. How does it, can you comment on the role of decoherence on the left-hand side of that relation?
Yeah. So, decoherence is basically the fact that whatever is outside of this system, right? So the environment starts to effectively destroy the qubits on the boundary, say, here, right? But this system has got this wonderful property that the information in the middle is very redundantly encoded. So basically, right, if I know the information on a sufficiently large portion of the boundary here, I'll know what's going on in the middle, even if I lose everything in the interior. So, which is a really cool thing if you're trying to build a quantum computer. So you try to do that. You try to basically implement some kind of error. It's called quantum error correction. You try to do something like that, right? This is an example of a network of qubits which constitutes an error correcting code. It's called the HAPP code, and it's such a thing. But it's also holographic. It's also got this emergent geometrical property.
I'm going to allow myself the last question. You started your talk motivating the black hole information paradox by appeal to the fact that the Hawking radiation is black body radiation and structureless. You solved the problem, it seems, by appealing to the holographic principle. So you have a quantum mechanical theory on the boundary, which is unitary. How does that affect the original conclusion that the Hawking radiation is structureless?
Well, it implies that it is not structureless straight away.
It's still black body.
Right? No, it is not black body. Okay. Right? There are correlations in the Hawking radiation. And you might say, well, okay, that's what it implies. So the holographic principle says it must be the case that there are correlations in the Hawking radiation. It's not black body. And in around 2019, 2020, that was demonstrated by explicit calculation for the first time. So it was shown that the entanglement entropy of the Hawking radiation goes to 0 at late times. Nobody, as far as I'm aware, really understands what is happening that should be the case. But there now is an explicit calculation which, and it in particular can point to the bit of the calculation in Hawking's calculation where there's a difference.
I see.
Right?
Thank you very much.
And it's really, that would be another talk to talk about that.
Sure. Well, thank you very much. Join me in thanking Professor Forshaw.